Today we're going to take a look at section 1.3, and 1.3 is going to be computing limits in a different way. So in section 1.2, how did we find limits? There were two things we did. Somebody tell me one of them. Graphically. So we looked at a graph, either a graph we were given or a graph that we used in our calculator, and we estimated using a graph. How else did we do it? Tables. We call that numerically. So we inserted numbers into our graph or our equation, right? And it came out with a list of numbers, and we put them into a table. So today we're going to compute them what's called algebraically. All right? Some of you were trying to do this ahead of the game last time, weren't you? So some basic limits that you should be aware of is that if you have the limit of a constant, or you're trying to find the limit of a constant as x approaches a, it's just the constant. And I just want to argue from a graphical perspective why this makes sense. If you had, and we'll put a number in here so that we can draw the graph in a way that is just a little easier to see. Let's say that this said the limit as x approaches 2 of the value 70, we'll just say 7, it'll be easier to draw. So the graph here is the graph of y equals 7, which would look something like this. Okay. So you've got a horizontal line, because that's what it is when you've got a constant, you've got a horizontal line. And the question is, as x approaches 2, what y value am I getting close to? Well, 7, because the entire graph is the number 7. Not very interesting. That's all this is saying, is if you have a constant and you want the limit of it, it's just the constant value. Okay. The next one, number 2, says the limit of x as x approaches a is simply a. Now, again, from a graphical perspective, this makes sense. This right here is the equation y equal x. So the graph of y equal x looks like this. It's a line. And when the equation is y equal x, then when you're at x equal to, let's say, 4, what's your y value?
4.
Yeah, it's 4. Because y and x are the same value since y equals x. So that's all this is saying, is that if you have the limit of simply x, it's just going to be whatever the x value is that you're approaching. If x is approaching 7, the y value is going to be approaching 7 as well. This is the linear rule. So these are the two that are the basic ones, the most simple ones. After this, we have 4 more that are very handy, and everything that we would want to be true in the world about limits is true about limit. So let's take a look at these. So we have a limit for f of x, and we have a limit for g of x. C is a constant. And then we have the following 4 limits. Okay, so I'm going to pause the recording. I'm going to let you write everything down, and then we're going to talk about them. Okay, these limit theorems, as some of you are noticing, look kind of funny. I mean, they look complicated. Some of the feedback I got real quick there. You said, I hope they're not as complicated as they look. So let's take a look at what's going on here. So we've got some function. So this is just some equation, right, that we're given. And we know it has a limit, right? So it's some equation that has a limit. All that this first one is saying is that if I multiply that equation by a number, I could do the same thing, and then I find the limit. I could have found the limit first and then multiplied it. It's just telling you that the order of that multiplication doesn't make any difference. Okay, you multiply it first, multiply it after, it doesn't matter. The second one, similar kind of feel, it's saying that if I have 2 functions that are added or subtracted together, what I could do is I could add and subtract the functions and then find the limit. But it's the same thing as if I found the limit of each of them separately, and then I added and subtracted the limit values. Okay? The third one's talking about that same thing with multiplication. Instead of multiplying the functions and then finding the limit, I could find each of the individual limits and then multiply them. Because I don't know about you, but it's easier to multiply numbers, which is what limit values are, than to functions, which is algebraic expressions, right, like equations. Last one is the division one, and it says if I've got 2 functions that are divided and I'm finding their limit, that I could have found each individual limits and then divide those values instead. And this last one has this extra sort of condition here at the end that the denominator can't be 0, right, because then we would have an undefined value. Okay, so does this sort of make sense? I'm going to show you how this works in practice, and you're going to be like, you almost can't even see that you're using these, but you are. So let's take a look right here. This one says we have the limit as x approaches 1 of negative x squared plus 1. Well, what this is actually telling us that we can do is I can find, and I'm going to write it out on this one so you can see where it's happening. On the next one, I won't write it, and we'll just talk about where it's happening. According to this previous slide, second one, the second property or whatever, second part of the theorem, this says I can separate this, and I can write the limit as negative x squared, and then the limit of 1. That's what it's saying I can do. I can separate those into two separate limits. The first piece on that previous slide is saying that that negative in front of the x squared could be moved to the front of the function. So I could put the negative outside here. And then if I use the third part of that theorem about multiplication, I can recognize that x squared is just x times x, right? So I could write this as negative limit of x as x approaches 1 times the limit of x as x approaches 1. And then I have plus the limit of x, of the limit as x approaches 1 of 1. So that previous slide actually allows this to be thought of in this sort of elongated way. But then each of those pieces that are there now go back to those very, very two first basic limits that we did over here, and we can apply them. Yes?
Is this all right to do? What I do is I just thought it as a difference of squares, so separated it out into 1 minus x, 1 plus x, and then you just take the limit of that, or you can separate them.
But then you could separate it further. Yeah, we're not going to keep separating things in a minute here, so bear with me. We're about to be done with this separating.
Okay,
yeah, you can do that. All right, so this, on this slide, let me say. So this slide, remember, talked about limits of constants. Well, we've got a constant limit of the number 1, and limits of x, and we've got two limits of x, and it's saying that I can plug in the number. So if you take a look over here, what this actually boils down to is saying that I have a negative on the outside here. The limit of x as x approaches 1 is 1, because I'm plugging in the number because it's x equals y. I've got another one of those. And then the limit of 1 is 1. So this boils down to negative 1 times 1, which is plus 1, which is 0. Now, in reality, so I wanted you to see where this is playing out. And I'm about to erase this and show you how we work the problem without showing all these pieces, because we don't need all those pieces, but they're hidden in the way that we normally do the work. Okay, so does everybody have this sort of written down as so you can see where those pieces are coming into play? Here's how the problem really works. Because we're able to simply plug the x value in for the x value when we're able to, we can do that here as well. One squared is 1 times the negatives. This is negative 1 plus my 1, and this is 0. So this boils down to being able to evaluate the function. Now the same thing we could do, we could do the same thing here on number 2, right? We could separate this into the limit of the top and the limit of the bottom. That's using property number 4. And then we could separate this into the sum and the difference on the separately on the top and the bottom. And then we could pull the 2 to the front because it's a constant multiplier. It's a constant that's multiplied. So we could do all that separation, but the net result of doing all that separation is the exact same thing that would happen if we evaluate this function at the value negative 3. All right, so what's 2 times negative 3?
86.
Minus 3?
39.
All right. On the bottom, negative 3 plus 5? 2. And negative 9 over 2 doesn't reduce, so we can leave it.
That's it?
That's it.
Okay, I see what you're talking about when you say you don't even realize.
You don't realize you're doing it.
I just feel like you're substituting.
It feels like you're substituting, yes. Now, it's not always possible to do that substitution. We'll see ones here in a minute where we can't simply plug the number in. But we actually are able to do that plugging the value in Because if the graph is one of the ones, most of the ones you've worked with have these properties, nice and smooth and continuous and all of that, then the limit value is just the y value. It actually gets there. It doesn't just get close to that y value, it actually gets to the y value. Okay? Now, the next graph is different because it's defined in a piecewise way. This graph says to find the limit as x approaches 1 from the left. Remember we did that notation last time, 1 with that little negative. And our function is defined in 3 different pieces. Okay? The 3 different pieces are surrounding the values of x equal -1 and x equal +1. So before -1, the graph looks like 2x plus 1. Between -1 and 1, the graph looks like the constant value 3. And then after the value of 1, the graph looks like, again, 2x plus 1. Okay? Everybody good so far? We can look at this from a graphical perspective, and that's fine, and we can do that. There's nothing wrong with that. But we don't have to, because we've got some of these properties. But what we do need to figure out is we do need to figure out that if I'm dealing with the limit as x approaches 1 from the left, which of these 3 pieces of this function am I concerned with? The first one, the second one, or the third one? Can you tell?
I'd say the first one.
Oh.
Because you're dealing with x when it's less than -1, which would be on the far
Be
right.
careful. It is the second one. You guys are getting mixed up with the negatives, I think. This limit as x approaches 1, not -1. Right? This says x approaches the value of 1, not -1. There's a lot of negatives going on in the problem. That's why I'm showing you this, is because you need to be careful to see where the negative applies. This is x approaching the value of 1, which means I'm on one of these 2 right here. Because this one is to the left of -1. It's far away, I mean, at least in theory. These 2 lines right here, the second line and the third line, are the 2 lines that are actually getting close to the x value of 1. Now, which of these 2 lines, that's the second line here in the middle that says 3, or the last line that says 2x plus 1, is actually 1 from the left? That's the second one. So the value of 1 from the left is on this middle line right here. Okay. So in terms of your graph, and I'm not going to draw the whole graph, but I'm going to draw the number line of what's happening to kind of give us some perspective. Here's -1 and here's +1. And our graph that we're looking at is sort of split up into 3 pieces. It has 3 different equations for the 3 different pieces of this graph. But if I'm getting close to x equals 1, but on the left-hand side, I need to be between the 2 vertical dotted lines that I've drawn in here. Well, the equation that applies for that piece of the graph is the equation at the line 3. So I just need the limit of 3 as x approaches 1 from the left, which is what? That's 3. Is that okay?
Right there at the end, what
Right there at the end, what
happened? The
happened?
limit 3.
This one?
Yeah.
Well, this right here, this limit as x approaches 1 from the left of the number 3 is simply that basic limit that we started out with. It's constant.
Oh.
So the limit of 3 is 3. That's what happened at the end.
Gotcha.
Now, just for kicks and giggles, let me show you what would happen if the question were worded a little bit differently. Let's say that it wanted 1 from the right. So if it wanted 1 from the right, which line of this equation set of equations would I be on? I'd be on the third one, right? Which means I'd be talking about the function that's expressed as 2x plus 1. So if I were doing that piece of this one, what would it be? It would actually be 3 as well, right? But for a very different reason, yeah?
Yes.
I'm using a different equation to find that. So if I were asked, again, the problem doesn't do this on this one, but yours could on the ones you do in class on your homework. What then if it asked you to find the limit as x approaches period flat out 1? Okay, we learned about this last time. If you're asked to find the limit at a specific value of 1, it means you have to compare 2 different limit values, right? The one from the left and the one from the right. which is exactly what the last two things were that I did. The one from the left was the value 3. The one from the right was the value 3. So if I were to then compare these for my function, this limit would also be 3 because they match. Okay? Any questions on that? I know I went above and beyond the call of duty on the questions directions, but I thought it was worth mentioning since your questions won't all look exactly like that one. All right, let's take a look at a couple more theorems. This next theorem, theorem 3.2, says that for any polynomial, okay, so do you remember what polynomials are?
X plus 1.
X plus 1 would be a polynomial. Okay. 3x squared minus 7x plus 2 would be a polynomial. Okay, so polynomials have whole number exponents on their variables. They can have addition or subtraction. It's often easier to think of what polynomials aren't and say it's not that. Like you define it by what you're not. I'm not this kind of a person, I'm not this kind of person, I'm not this kind of a person, right? Polynomials are kind of like that way too. Polynomials do not have exponents that are fractions or decimals. They do not have square roots. They do not have variables and denominators. They have none of that. What this is saying, though, on this one is that if I have a polynomial and I want to find the limit as x approaches a, I can plug the value for a in. And the reality is I did that over here on number 1. I actually did. And I showed you why it worked, because I used those limit theorems from the page before. So you can actually do this all the time, and it works all the time without separating it out into all of the pieces that we encountered. Theorem 3.3 says that if you have the limit of an nth root, so like a square root or a cube root or a fourth root or something, and you want to find that root of the function's limit, the limit of the root of that function, then you could take the limit first and then find the root afterwards. Okay. It's kind of like what I did with the squaring, right? I could take and find the square value first and then put the negative on afterwards with a coefficient. Okay, so you can do all of the operation first and then square root it afterwards. So we're going to practice on a couple of these. Might be worth noting that the limit value actually needs to be positive. L has to be greater than 0 on this for this to work when n is even. Think about square roots. You know you don't take square roots of negative numbers, right? Yes? Okay. That's what this is talking about. And it's not just square roots. It's any kind of an even root. So square roots, fourth roots, sixth roots, eighth roots, any of those. So if we had an even root, we would need to have a positive value underneath. In reality, we could actually have the equals here, and it would be okay too. And so let me go ahead and put that in. I think that's a typo, because you could take the square root of 0. That's okay. But you can't take the square root of a negative. So it's actually L is greater than or equal to 0. All right, let's do some examples. This says, find the limit if it exists. Now, on number 4, we're going to try and do what some of these others have said we can do. I know that this slide over here didn't say anything about rational functions, right, where it has a numerator and denominator. But the reason it didn't is because we already had that theorem over here on number 4 where it says, look, I've got something on top, I've got something on bottom, I can separate those two limits. And then if I separate those two limits here, I've just got a polynomial on top and a polynomial on bottom. So I can kind of combine that polynomial theorem with the part 4 of that previous theorem, and I've got the pieces that I need that all allow me to say, I can just try and plug the number in. But hopefully, as we do so, you recognize this is going to have a problem.
0, 0.
Yeah, I get a 0 over 0. That's a problem. So, some of you already know what we're going to do. So somebody tell me, what are we going to do if I end up with that 0 over 0 business going on? Any thoughts? I'm going to factor. Yep. So when I get 0 over 0, what it means is something's factorable. I mean, that's what it really means. So we're going to attempt to go back and factor. Now, the numerator doesn't really, I mean, there is another way I could write it, but it doesn't truly factor into anything different. But the denominator will. What will x squared minus 9 factor into?
X plus 3 plus 3 plus
Yes, x plus 3, x minus 3. Now, between the numerator and the denominator, there are two of them that look similar. They don't look identical, right? I've got 3 minus x on top, and I've got x minus 3 on bottom. Agreed? How are they different?
One's got a negative for the numerator.
Yeah, if you take a look, they're exactly different by a factor of -1, right? So I'm going to do something that's going to look a little bit odd in terms of how I normally would factor, but I'm actually going to pull out a -1 from the top. And if I do that, it will change both signs, which means that instead of having 3 minus x, I will actually have x minus 3. Right, if you multiply that negative back through, right, you'll end up with the 3 minus x you started with. Whether you show that you've pulled that negative out in that way or not doesn't really matter to me, but that negative better show up in your answer because it's going to affect the answer to the problem. So this problem ends up becoming the limit as x approaches 3 of -1 over x plus 3. Now can I plug the value for 3 in? Absolutely can. I have -1 over 3 plus 3, which means my limit is -1 over 6.
And the fact that we factored that out,
Mm-hmm.
graphically, would that mean there'd be a hole?
That's exactly right, and that's the next thing I was going to say. So if you have the ability to do what we just did and factor and reduce, what that means is that in that graph, there's a hole in that graph. The function value does not exist there, but the limit still does. It still gets very, very close as you could possibly want to the x value or the y value of -1/6. But there's a hole in the graph. Okay? Take a look at number 5. What happens when I try number 5? Yeah, I get 0 over 0, right? This is my try. So that's not good. I mean, that's obviously not my limit. Either I need a factor or I've got another problem. But the fact that it's 0 over 0 means it's going to be able to be factorable and simplify. So let's take a look. I need to factor the numerator. Can someone help me with that?
X minus 4, x minus 1.
X minus 4, x minus 1.
Okay. I think both of you said that one, right? Okay. Does that work? Everybody else check that? Okay. All right. Somebody else now. Denominator.
X minus 4, x plus 2.
Good. Now, some of you probably don't like factoring. That's okay. The nice thing about the factoring that we're doing right here is that the factors going to have to have this 4 in it. Otherwise, it's not going to help me in terms of the problem. Do you guys see that? The problem in getting the 0 over 0 is in coming in with the fact that if I plug in the number 4, I get 0. Well, that means I'm going to have a factor of x minus 4 go away for me to continue with this problem. Because if it doesn't, then I'm still going to have 0 over 0. And sure enough, if I have that x minus 4, notice if I plug in 4 to that piece, that gives me the 0 that's causing the problems, right? So the fact is that because I'm doing my limit as x approaches 4, there's an understood feature to this that says one of my factors is going to be x minus 4. It has to be. So that can kind of help you in determining your factoring too if it's more complicated than you feel comfortable with or don't remember pieces of. So I've got to reduce this. I will then have the limit as x approaches 4 of x minus 1 over x plus 2. And now I can evaluate that at the value 4. So I have 4 minus 1 over 4 plus 2, which gives me 3 over 6, or 1/2. Now, I want to draw your attention to something, and you can go back on the work that you're doing right now and decide if you did it or not. And if you didn't, you can include it, and then on your homework you'll want to. I want you to notice that I write limit as x approaches 4 every time I'm still working with the value x. So if x is still in the problem, the limit's still in the problem. The point when I stop writing limit as x approaches 4 is exactly the same point when x is actually written as the number 4 in the problem. So if you still are writing x over 1 or an x in the fraction or in the polynomial or whatever, you should have a limit in front of it. And if you're no longer writing x in the problem, you no longer need the limit notation in the problem. Do you guys see that? And I did it on the problem before too, right? You see the original problem, you see all my factoring, all of them have limit because they still all have an x involved. Right here even, limit as x approaches 3 of negative 1 over x plus 3, still got an x in it. The exact point when I stop writing limit is the exact point when the x is replaced by the number 3. It's not an accident. That's proper notation, and I'll expect to see that on your papers as well. All right. This one does not look like the last two. However, if I try to plug in the 0, because as x approaches 0, what's going to happen?
Square root of 2.
I'm going to get
Minus square root of 2.
square root of 2 minus the square root of 2.
So you can factor it.
Yeah, so it's got a 0 over 0, which means there's going to have to be some kind of a way to get rid of the fact that I'm getting the 0 over 0. There's got to be some sort of a factoring going on. But I've got square roots, and so it isn't going to look like factoring. All right, so I want you to jot yourself a note that when you see this kind of a notation, what the issue is the issue is about rationalizing. Now, you're probably more used to the phrase rationalize the denominator, right? Probably did it in trig, probably did it in algebra. What we're going to do here is we're going to rationalize the numerator. Now, you may be like, why would I want to do that? Well, it's going to work is why. So bear with me, and I promise in the end it'll all be worth it because it'll actually work for us. So in rationalizing, do you guys remember how to rationalize when you have an ugly expression like square root of 2 plus x minus square root of 2? What do you do to rationalize?
Multiply by the conjugate?
Yes, conjugate. Very good. All right, so conjugate is the same expression with the opposite sign. So that numerator, that long numerator with all the square roots, we're going to use that same numerator, but instead of having a minus sign, a subtraction sign between the two terms of square roots, I'm going to have an addition sign. So I'm going to multiply by square root of 2 plus x plus the square root of 2. And in the denominator, I'm going to do the same thing. I'm going to multiply by square root of 2 plus x plus the square root of 2. Now, let me notice with you that what that does in the denominator is it means that that new piece that I just multiplied by, I can plug 0 into that. Right? Like I couldn't plug 0 into the original one because it's simplified to 0 because it was subtraction. But when I plug it into this addition one that I just created, it's going to actually end up not being 0. Okay, so that's a good thing to notice here. The other thing to notice is that while this new denominator is going to be multiplied by the x, I don't really want to distribute the x. That would not be a helpful thing to do. So we're going to leave it in factored form because just like you guys mentioned before, it's going to factor. What's going to factor out is that x. Okay, so that's my denominator. I'm not going to simplify that denominator. It needs to be written ugly, just like that. Now the numerator is going to simplify. The whole reason that we chose this numerator is because the square roots will go away when I simplify it. So if I were to FOIL this, right, multiply first, outer, inner, last, the first terms when they multiply are square root of 2 plus x times square root of 2 plus x. So what happens when I multiply two square roots that are identical underneath them together? You get rid of the square roots. You get the exact value that was under there to start with. So that gives me 2 plus x without the square root. Now take a look at what happens when I do the outer term and the inner term. Square root of 2 plus x times the square root of 2. And then the other one is square root of 2 plus x times the square root of negative, or the negative square root of 2, actually. I said that wrong, but negative square root of 2. It's the same multiplication, except what? One's positive and one's negative. So what happens when you have the exact same thing, one's positive, one's negative? They cancel. That's why we chose this particular expression to multiply by, is because the outer and the inner terms cancel. Okay? You also see it happen with difference of squares. That's sort of the underpinnings of what's going on there. All right, the last terms now. All All right, so my last terms, these two. What happens when I do negative square root of 2 and positive square root of 2?
-2.
That's negative 2. Beautiful things are about to happen. Are you so excited?
Yep.
All right. First thing, what do you see happen on top?
Is X.
Okay, can't deal with the x just yet. Something before that on top. 2's go away. I've got a positive 2 and a negative 2, right? Yes, I do. So this and this go away. Notice I'm still writing limits, and you should be as well. Now I have x over x times 2 plus x underneath the square root plus another square root of 2. Now what happens to my x's?
Cancel.
The x's can cancel. There's that factoring you guys wanted to do, or at least that reducing. So these x's cancel. That does not mean there's nothing on the numerator now. What's in the numerator? 1. So be careful. Don't go and tell me that now the numerator doesn't happen or something. And the denominator is square root of 2 plus x plus the square root of 2. And just like we talked about before, it is perfectly fine now to plug in 0 to that denominator because it's not subtraction, it's addition. So I end up getting 1 over square root of 2 plus the square root of 2. We're going to simplify that a little bit. So what's the square root of 2 plus the square root of 2? 2 square root of 2. We're not going to leave it with a square root in the denominator. So from trig, you know what to do because square root of 2's happened in trig a lot. What do I do with that square root of 2 in the denominator? Rationalize it. Do you remember how?
Square root of 2 and square root of 2.
Right. We'll multiply the top and the bottom by square root of 2. Oops. So I get square root of 2 on top. And then on bottom, the first 2 right here stays. It's multiplication. And then we already did square root of 2 times square root of 2 a minute ago, and you knew that one was 2. So I end up with square root of 2 over 4 as my final answer.
So you want us to always rationalize those?
Yeah, yeah. There will be a few times in our class where we don't rationalize something, or at least it appears that way, and I'll make mention of it when that happens so that you can see why it's not the same situation. Yeah. All right. I keep hearkening back to trig. We're going to do just a touch on trig right here next, okay? If we have sine function or a cosine function and we want to find the limit at an x value of a, we do the same thing that we've done on polynomials and rational functions. We're able to plug the value of a in for this value. So the limit of the sine of x is going to be the sine of a. And the limit as x approaches a of the cosine of x is going to be the cosine of a. And this happens very much for the same reason that it worked for polynomials. Sine and cosine curves are nice and smooth and continuous. There's no holes, there's no jumps, there's no asymptotes, none of that's going on. This is a special trigonometric limit, okay? We're not going to get to the point anytime soon where I'm going to show you why that this is a true statement. So we're just going to use it at the moment, and we'll talk about it. I can't even remember if it's in this class or in Calc 2, where we talk about why this works. But the limit, obviously, if you tried plugging in the number 0 here, this wouldn't work. Sine of 0 is 0. X is 0. I'm going to get a 0 over 0 here, okay? But the reality is, with simplification and the way we do this particular problem, I think it actually is towards the end of this class, that when we plug in, or when we talk about how to actually find this limit in a different way, we will find that this limit value actually is the number 1. Okay, so... No, it's something else. Okay, but we're going to use this fact on the next problems. All right, so let's take a look here for starters. Number 7 and number 8. Number 7 says we want the limit as x approaches 2 of the sine of pi x over 2. So, what are we going to do? Plug in 2. So, I don't need to write limit again because I'm actually going to plug this in. This is the sine of pi times 2 over 2, which is the sine of what? Sine of pi. Now, if you don't remember, in the front flap, I think, or maybe the second page of your book, there's a unit circle. Okay? Sine of pi is, somebody said it already, is 0. Okay? I am not going to require that you rememorize your unit circle, although I think it would be a good thing for you to remember if you do. If you don't have it memorized or it's been a little while, you might want to, for the next few sections anyway, have a unit circle with you as you're working, okay? Or have access to one if you want to pull it up on the internet if you're working at home or something like that. All right, the next one, the limit. As x approaches 5 pi over 6 of cosine of x, what would I do? Cosine of 5, pi over 6. That one might not be on the tip of your memory as much as the last one. Do you know?
Negative square root of 3 over 2.
You got it. 2 of you got it. Awesome. Negative square root 3 over 2. No worries if you're not remembering at this exact moment. It kind of sprung it on you all in the middle of class. That was pretty good.
What would that be in degrees?
This is all in radians. Everything we do is in
What
radians.
would that be in degrees? Just like,
Oh, what would that be in degrees? The 5 pi over 6? Do you guys know?
just so I can visualize it in my mind.
Is that, it's right before pi, whatever
Uh-huh.
that is.
100, 180, or 150.
150.
Yeah, it'd be 150
Okay,
degrees.
cool, that makes
Yeah,
sense.
yeah, it would. Yep. Okay, now let's see an application of that funny trig limit. This one says the limit as x approaches 0 of sine x over 5x. Now that looks an awful lot like this special trig limit, right? What's the difference?
Multiplied by 50.
There's a 5 in the denominator. It's multiplied by 1/5. So what we do is we're going to rewrite this using a property that we saw at the very beginning. That said if I have a constant multiplier, I can pull it out in front of a limit. So I can rewrite this as 1/5, the limit as x approaches 0, of sine of x over x. And then I can use that special trigonometric limit to say that the limit as x approaches 0 of sine x over x is 1. So this ends up being 1/5 times 1, or 1/5. What's going on 10?
Something crazy.
Something crazy. There should be, as you look at this, something that says, now wait a minute.
Oh, that's
What
just
is it?
sine of x over x.
It will be in a minute. But looking at it as it's given, what part of this should make you say, now wait a minute?
Tangent.
Tangent, because I haven't talked about tangent, have I? Okay, so we need to do something with tangent to turn it into something with sines and cosines, because that's all that we've got to work with right now. And in reality, tangent's not very friendly, because tangent has lots of asymptotes, doesn't it? So I don't really want tangent involved here. I would like to make it not involved if possible. So yeah, I need to change that tangent. So some of you are already telling me how to change it. So somebody tell me out loud. Oh, good. So tangent is sine of x over cosine of x. Now, I didn't teach any of you guys trig, but I do want you to remember that when you write sine and cosine, they don't mean anything without what's next to them, that angle. So this is the sine of x. It's not just sine. It's like saying square root. Square root of what? If you don't tell me square root of something, square root doesn't have any meaning. Sine doesn't either. Okay, so make sure you've got that x next to it. What simplifies?
Cosines cancel.
Cosines cancel, which means this problem actually becomes the limit as x approaches 0 of sine of x over x, which has a limit value of 1. All right. How is 11 different from every other problem we've done?
Got 2 functions.
It has 2 functions. That's one way. There's something else, though.
Oh, it defines like a function is a function.
It's got a function inside a function. Still not what I'm hoping you're going to see. Keep going. You're saying correct things, but what else?
Division and the power.
We got division and powers. Oh, you guys are coming up with good stuff. But you've overlooked the biggest thing going on.
You're having to reference, use one function. to find another
It
one.
tells you what the limit of g of x is.
This one tells us the limits of g of x and f of x. And it has to. Why?
Oh.
What does this one not do that everything else did?
It's not telling us what it approaches.
No?
Can you just use one of the rules that they gave us to do limit of f of x?
Yeah, we are going to. It doesn't give you any equations. Do you guys see that?
Oh, yeah.
There's no equations on this one. All I have is f of x, g of x. I'm not told what they are. They aren't sine of x. They aren't x squared plus 3. They aren't square root of 2 minus 5 or whatever we had. They aren't any of those things. They're just written in notation that says f of x, g of x. And because of that, we do have to use the rules we were using before. So let's go ahead and write those out, because that's what this problem is actually wanting you to do. We talked about when we were actually dealing with equations that it's sort of hidden. You can't really see how the pieces are sort of really playing out from those properties. But when we're dealing with this problem, we are going to see it, and we're going to need to use it. So the first thing you guys mentioned is you have a quotient, right? You have a numerator, you have a denominator. So the first thing I'm going to do is I'm going to rewrite this by separating the numerator from the denominator. You're using properties to do this one. Okay? You have to show what I'm showing right here, and I'll tell you why in the end that it wouldn't work to do otherwise. So let me keep going. I know the limit of g of x. It's -3. They gave me that information. But the information they give me about f of x can't be applied yet because this says f of x is squared. So what do I have to do to rewrite the numerator now?
Do it twice.
Do it twice, yeah. It's multiplication, right? F of x is multiplied by itself. So this is the limit as x approaches a of f of x times the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. You have to get it into this form because this form is where the substitution happens. This piece of information right here, the limit of x approaches a of f of x equals to 2, is now able to replace these two pieces of information because they're identically the same. We didn't have that before. You can't just plug in the number 2 up here on top and square it into the original function because it's not the function value, it's the limit value. It's not the function value, it's the limit value. So we have to get this expression to be written in terms of individual limits to apply those limits properly. So what I do now have is I really do have 2 times 2, and my denominator is -3, which means my answer is -4/3. But the in-between steps have to be there, otherwise it doesn't make sense. Your substitution would be incorrect. All right. Occasionally in your homework and occasionally on exams or your reviews, we'll see problems where they ask you to create an example. And your example may not look like someone else's. There would be multiple versions of examples that would work. But this example wants us to create functions, f of x and g of x, where the limit of the two added together works, but the individual limits don't. Okay? Now, this sort of is taking what we are being told back in theorem 3.1. So if you flip back to the very front of your sheet, theorem 3.1, part 2 said that if you know the individual limits exist, then you know that the sum of the limits exist, right? This example is telling you that there is a way to create something where the sum exists, but the individual ones didn't. Basically, it's saying that you can't take theorem 3.1 and go backwards. You can't start with this result and actually get back up to function values that are for sure going to have limits. Okay? So I'm going to give you an example of one that would work on this. And you're going to be like, oh, well, that was simple, but maybe you wouldn't have thought of it. What I want to do is I want to take, my function f of x to be 1 over x. And I want to take my function g of x to be negative 1 over x. So the first thing I'm supposed to have to show is that the limit, when I add them together, and we'll do as x approaches 0, that the limit when I add them together works. So if I take the limit of f of x, which is 1 over x, plus g of x, which is negative 1 over x, as x approaches 0. What happens inside of these brackets?
Cancels out.
Yeah. 1 over x and negative 1 over x add to 0. So this is actually the limit as x approaches 0 of 0, which is a big whopping 0. Okay? However, the limit as x approaches 0 of the individual limits.
How did your 0 turn to
It didn't. It's just sloppy handwriting. I will make it clearer. There you go. So these are my individual limits from f of x. So f of x is 1 over x. G of x is negative 1 over x. What happens here if I have to try and put 0 into the denominator? It's undefined. And it's not undefined in the way that the other ones were. It's not 0 over 0, right? It's 1 over 0. So this limit doesn't exist. And I'm going to show you from a graphical standpoint as well why that makes sense on these last two pieces right here.
I have a question.
Mm-hmm.
Okay.
Okay, what's your question?
Where, you kind of lost me at the beginning. Like, where did you come up with your 1 over x?
I created them in my mind.
Okay.
It just says give an example. And I told you I was just going to give you an example that shows you an example of how this could happen. So what I wanted is I wanted something that when they add together, they go away. Because if they're going to go away to 0, then the limit's going to automatically exist. But I wanted them so that when they're separated, the individual limits don't exist. So one of the ways that individual limits are not going to exist is if they have asymptotes. So this graph of 1 over x looks like this. Oops, that was not very good. Let's try that again. So if this is the graph of y equals 1 over x, and if x is going to approach 0, here's the line x equals 0 right here, the y-axis. It means I need to get close to 0 from both sides. You see a problem with that? On one side it goes to infinity, and on the other side it goes to negative infinity. Okay. And this graph would just flip upside down if I put a negative in front of it, which is the g of x function I created. So I'd still have the exact same problem. Where as I'm getting close to the x value of 0, which is the y-axis, one side I'm going up and the other side I'm going down. So this does not have a limit because it has an asymptote there. So in my mind, I was trying to create something that had an asymptote, but when I added the things together, the asymptotes disappear because the functions added to 0. And this was an example that would do that.